Now, vectors, with vectors, oftentimes we're interested in figuring out what portion of one vector goes in the direction of another vector. So the picture you should have in your head for component and projection, let's say that this is my vector v and my vector w. So what we want to know is somehow, like, if v is the ground, what is the shadow, and the sun is sort of directly above, what is the shadow that v is going to cast along, the shadow that w is going to cast along v? So the component of w along v, so that's v is the subscript, it's the ground, and v is the thing that's shooting up into the air, and we ask what is the shadow that w casts along v. And we've been through the formula before, but just so that you have the picture, the idea here is that you drop a perpendicular to the vector v, so this should be a perpendicular, and what we ask is how long is this line segment that starts at the beginning of v and goes only until the shadow of w. All right, and we know that we have a formula for this. It is magnitude v, magnitude w, divided by the magnitude of v. We've been through this formula before. It is v dot w divided by the magnitude of v. The way that I always remember this is it shouldn't matter how long v was to start with. If v had gone twice as far, this line segment would still be the same length. And so in the formula, you see that you're dividing, you're taking a dot product with v, but then you're dividing out by the magnitude of v, so that's what makes it so that the magnitude of v is inconsequential. Okay, and you wouldn't divide by the magnitude of w because then it would say that the length of w is inconsequential, which is not. If you double the length of w, you get a longer shadow. The projection is simply turning this line segment into a vector. And we have a formula for that as well. So the projection of w along v is simply v dot w over magnitude of v squared times, so this is going to be a scalar, and you multiply the vector v by that. Or if you prefer it the other way, it's the component of w along v multiplied by v divided by its own magnitude. Now, I think it's probably better just to keep this formula in your head. But if you have a hard time with it, you can remember this formula as well. Moving on to vectors in physics, the most common situation in which we see vectors in physics is forces that are acting on an object. Or if we've divided everything by the mass, we could just say the acceleration on each of the acceleration that would be caused by each of the forces. So this type of situation shows up when we want to balance forces. So if I have an object that I want not to be moving, or rather I want an object that is not experiencing any acceleration, then I need to make sure that the forces acting on that object are what are called balanced. And what it means for forces to be balanced is that when you take them as vectors and take their sum, you should get, as a result, the zero vector. That's the vector where you have all zeros. Okay, and we've seen examples in the homeworks about balancing forces, but primarily what you need to be able to do is take a collection of forces, and if you want to balance them, you set the sum of the forces equal to 0. One thing that you probably need to know about that is that if you have an object of mass m just hanging out near the planet, near Earth, then the force due to gravity acting on that mass is 0 is the first component, and negative 9.8 times the mass is the second component. So we know from Newton that if you multiply mass by acceleration, that gives you the force, and the acceleration due to gravity on Earth is constant, and its value is negative 9.8 meters per second squared. So that's what it allows us to always figure out what the force due to gravity is acting on an object near the face of the Earth. The only thing that could change is if we are on a different planet, for example, this force due to gravity, this multiplier would be different, but it would still be multiplying the mass. Work, we talked about work. I may ask about work. The definition of work is very simple. Work is equal to, if you have a force that's constant acting on an object, and it causes that object to move a displacement of d, you take the dot product of the force and the displacement, and that produces for you the quantity of work. The measurement is in joules. So that's one thing to keep in mind. Those are the units that we use, or sometimes Newton meters. So if you start at a certain place, let's call it P, and you end at a certain place, let's call it Q, and you've traveled in a direct line from the one to the other, you can take PQ to be your displacement vector. And suppose you have a force that was acting on the object with the same magnitude and direction the entire time until we stop, then the work that is done on the object in the motion is the force vector dotted with the displacement vector. Roughly speaking, it's a measurement of how much energy needs to be put into the system to change the location of the object using a constant force. So that's work. Now, we'll move on to this interesting definition of what's called the determinant. The determinant is this weird beast that takes as its input a square matrix and sends as its output a real number. The definition, very quickly, recall determinant of a 2 by 2 matrix. ABCD is AD, minus BC. The determinant of a 3 by 3 matrix goes like this. You take the 1, 1 entry and multiply it by the determinant of the submatrix that you get by destroying that row and column, E, F, H, I. You take the 1, 2 element, which is B, multiply it by the determinant of the submatrix D, F, G, I, the stuff that's left over if I destroy the column and row corresponding to B, and C times the determinant of the matrix that I get by removing the column and row corresponding to C, which is D, E, G, H. And then there's a sign convention. We flip the sign of the second summand, so plus minus plus. So I like to go through, had this red thing home about, I selected the A, destroyed the row and column with A in it, and took the determinant of the remaining matrix here. The determinant has some interesting geometric properties. It measures something. For one thing, if you hand me two vectors in two-dimensional space, this is in R2, that'll be different from our statement in R3. If you build a parallelogram and just tell me the vectors that are created by two of the sides, let's call this V and W, then the determinant of the matrix you get by putting V and W as rows, it also works if you put them in as columns. That's one fact about the determinant. The determinant of this matrix measures the area of this parallelogram. So if you wanted an area of a triangle, you could do that by just doubling it into a parallelogram and then taking half of whatever the determinant gives you. I should be a little bit careful. This is not just the area, it's the so-called signed area. So it could be negative, it could be positive, depending on the orientation of V and W. All right, on the other hand, if you are in three-dimensional space, the determinant, you can do two things. One is if you have what's called a parallelepiped. So it's a solid which has as its sides parallelograms. So all of its sides are parallelograms. This is a three-dimensional solid, and it turns out that any such three-dimensional solid can be created by just picking out the three vectors that meet at a corner and then taking sort of translations of those. So the bottom one could get translated to the top, and that makes the top of the box, and the one that's vertical goes to the back, and that makes the back vertical line, and so on. So if these are the vectors u, v, w, then the determinant of the matrix that's formed with u, v, and w as the rows, or alternatively as the columns, it turns out not to matter, is the volume. So it's the volume of this entire solid. Okay, and again, it's not just volume, it's actually signed. Depends on the orientation. So there's signed area from two vectors in two-dimensional space. There's signed volume in three-dimensional space with three vectors. And on the next page, we'll talk about how we use that. The cross product is given vectors v and w in R3, v cross w is the vector that you create by taking the determinant of the matrix, whose second row is v, whose third row is w, but its first row is I, j, k. Remember, I is this vector which has a 1 as its first component and zeros elsewhere. J is the vector that has a 0 and then a 1 in the second place, and k is the vector that has 0, 0, 1. And the nice thing about this definition is that when you calculate this thing, v cross w is perpendicular to both v and w. So we can use it, for example, if we know that there are two vectors that live in a single plane. So suppose we have two vectors that live in a plane, we can use their cross product to be a normal vector for our plane, and that'll help us build the equation for the plane.